All right, so today we're going to talk about probability and the binomial distribution. I think this is your first formal introduction to probability in the course, as well as to distributions such as the binomial or the normal distribution, which is something we'll cover later. But probability is really important to have a firm understanding of because it's something we'll use again and again as we go through the course, and it's really the core of statistics. All of statistics is trying to figure out how likely it is that certain things will happen, and probability is underpinning all of that. And the binomial distribution, you'll encounter many distributions in statistics. This happens to be a very common one, and one that really relates quite intimately to the discrete coin toss experiments that we'll be talking about today. So what is probability? Well, the definition has to do with the frequency with which something occurs. So if the probability of an event H happening is the number of times that H will occur divided by the number of times that an operation in which H could occur is repeated. And this is as the number of operations goes to infinity. So what does that mean? Let's think about the simplest example, which is a fair coin. There's a 50% chance that you get heads and a 50% chance that you get tails. Now, this does not necessarily mean that if you flip a coin 6 times, you're going to get 3 heads and 3 tails. You could get 5 heads, you could get 6 heads, depending on how lucky you are. But it does mean that as if you were to flip that coin infinity times, about half of those times would end up being heads, and the other half would end up being tails, if the probability of getting heads is 50% and the probability of tails is getting 50%. And so I ran a simulation which did essentially that. So 1 here is representing heads, and 0 here is representing tails. And this blue line is the ratio up here. It's the number of times that heads has occurred divided by the number of total times that I have flipped the coin. And for the first 100 or so, it trends downward. There are many more tails than heads for the first 100, but after that, things started to rebound, random chance set in, and eventually this ratio of the number of times heads has occurred divided by the number of times the operation has been repeated trends towards that 50% value that you would expect to see for a fair coin, with 50% ratio of being one thing or the other. So that's what this limit means. And the way we denote this in statistical terms is a p with a squiggly and an h inside of it, another squiggly, and equals 0.5 for heads and 1 for tails, right? So heads, tails, 0.5, 0.5. All right, so this is the basic definition, but this comes with a bunch of rules. The first rule is that this probability must fall somewhere between 0 and 1. If the probability is 1, that means the event always occurs. If its probability of heads is 1, then every time you flip that coin, even up to infinity, it's always going to be heads. Conversely, if the probability is 0, that means it will never happen. Every time you flip that coin, if its probability of getting heads is 0, you'll never get heads, it will always be tails. And everything in the middle is somewhere in the middle, right? If it's 0.5, it's half and half. If the probability is 0.7, then it's more likely to happen than not. If it's 0.3, it's less likely to happen. Everywhere along that spectrum. The second rule is that for every expected outcome from E1 to as many outcomes as you can expect, EK, right? E1, 2, 3, 4, 5, 6, 7, whatever. The sum of the probabilities of all of the possible expected outcomes is going to equal 1. So for this coin, right, there's 2 possible outcomes. There's 2 possible expected outcomes. One is heads and one is tails. The probability of heads is 0.5, which means the probability of tails must be 0.5 because these are the only 2 options, so they must add up to be 1. If there were 3 options, or if there were 6 options, like a dice, and 5 of the options added up to 0.8, the last option must be 0.2, right? Because it always has to add up to 1 for all the expected options together. And the last rule is that if there are 2 independent events, E1 and E2, the probability of both of these events occurring is the probability of E1 multiplied by the probability of E2. And a cool way to look at rule 3 is if you flip a coin multiple times. And if you're going to flip a coin multiple times, it becomes very useful to learn how to use a probability tree. So probability trees are where you map out all of the possible outcomes in a tree. So if we were going to flip this coin twice and ask ourselves what's the probability of getting 2 heads or a heads and a tails, we essentially add on another layer to this tree. So if we flipped heads, then we can get heads or tails. If we flip tails, we can then get heads or tails. And if you were trying to see what the probability of getting a heads and then another heads, which are 2 independent flips, it would be the probability of a heads multiplied by the probability of a heads given another heads, which is what this vertical line means. And that would be 0.5 multiplied by 0.5, which would be 0.25. If we were looking at heads and then tails, it would be the probability of heads, which is 0.5, and then the probability of tails if heads has already occurred, which is 0.5, and you'd end up with 0.25. Tails and then heads would be the same thing, 0.5, 0.5, tails, then heads. And if we were seeing tails and then tails, it would be 0.5 and 0.5 for tails, and then tails given tails. So that's how this rule 3 works out. If there's 2 independent flips, you're just multiplying them together to get the ultimate probability. All right, so there's one last rule here, rule 4. And that's that the probability of an event not happening is equal to 1 minus the probability of that event happening. The C in this stands for complement. The complement of an event is that event not occurring, right? So if your event is heads, right, the complement of heads is tails. If your event is rolling a 6 on a dice, then the complement of rolling a 6 is rolling a 5, 4, 3, 2, or 1. Any of those others is not rolling a 6, right? And the probability of not doing something is 1 minus the probability of doing that thing. So if we had a coin that had a 70% probability of flipping heads, then you would have to do 1 minus that. It would be a 0.3 for flipping tails. All right, so let's do an example. What is the probability of flipping 1 heads and 1 tails on 2 flips, given that the probability of flipping a heads is 0.7? This is where this concept of a probability tree really starts to pay off. So now it's not as simple. Not everything is 0.5 and 0.5. And if we draw out our probability tree, we can see just how this plays out. If we're going to get a heads and then a heads in this case, it would be 0.7 multiplied by 0.7, and we get 0.49. If we were doing a heads and then a tails, it would be 0.7 multiplied by 0.3. We get 0.21. If we were going to do a tails and then a heads, same thing, but reversed, and then we get 0.21. And finally, if we were going to do a tails and then a tails, it would be 0.3 multiplied by 0.3, which would give us 0.09. And so you'll note that all of these add up, 0.49, 0.21, 0.21, 0.09, they add up to 1 again, which satisfies rule 2. Everything falls between 0 and 1, which satisfies rule 1. All of these things that we're doing 2 of are multiplying together, which satisfies rule 3. And the probability of not rolling a head or not flipping a heads and then a heads would be adding up all of these other things together. And to the answer of our problem, the probability of flipping 1 heads and 1 tails, we can do that in 2 ways, by doing heads tails or by doing tails heads. And so we would add these 2 together. 0.21 plus 0.21 is 0.42. Okay, so what are some features of this coin toss experiment? How many outcomes do we have? Well, it's a binary outcome. There's 2 possible outcomes for each trial. Does the probability of success change? No, the probability of flipping a heads was the same each time. Does one outcome depend on another? No, we mentioned they are independent. If you flip heads on one, it doesn't mean there's going to affect the next flip whatsoever. and is the number of trials known in advance. And in this case, we said that we're going to flip the coin twice, and so yes, we did set the number of trials in advance. And these 4 fundamental questions are what determines a binomial random variable. A binomial random variable, which makes a binomial distribution, is something that has binary outcomes, 2 possible outcomes. The probability stays the same each time. The outcomes are independent, and we know the number of trials we're going to do in advance. And so I've thrown this new word at you now, random variable and binomial, but let's tackle random variable first. So what is a random variable? It's kind of like what it sounds like. It's a variable that takes on a value depending on a chance operation. So we've been using it this whole time, but it's the uppercase x instead of the lowercase x. X is a variable. X can equal 1, x can equal 5. Uppercase x is a random variable, and random variables have a set range of possible values. For the coin, it was a 0 or a 1. So that x equals a 0 or a 1. You don't know what it is until you flip the coin, and the uppercase denotes that you have not flipped the coin yet. You don't know what that uppercase x is going to be. So what about binomial? Well, a binomial with n trials is like the coin flip, where we have a probability of getting heads is 0.7, a probability of getting tails is 0.3, or 1 minus 0.7. And so we drew a probability tree for figuring out how many, what the probability of getting a heads and then a tails would be, or 1 heads and 1 tails. But what if we were flipping the coin 4 times, or 6 times, or 12 times, or 100 times? Drawing out those probability trees would be ridiculous and horrible, and I don't want to do it, and you don't want to do it. But we have to be able to figure out these types of problems, and luckily there are very elegant math solutions that have been developed. So let's see if we can kind of figure those out on our own. So what's the probability of getting heads, heads, tails, tails? Well, we said that heads is 0.7, so it would be 0.7 times 0.7 times tails, which is 0.3, 0.3, and we get a small number, right? So that's for getting heads, heads, tails, tails. But if we were to do tails, heads, it would be this same multiplication, just the numbers would be rearranged in order, right? So no matter what order we put these in to get 2 heads, we're always going to end up with a probability of 0.0441. So what if we wanted to ask the question, for 4 trials, what's the probability of getting 2 heads? Not just in this one order, but in any possible order. Well, for that, we'd have to count out how many different orders there are. You can do heads, tails, tails, heads, heads, tails, heads, tails, heads, tails, tails, whatever. All of these. There's 6 possible orders of heads and tails, all of which can get you 2 heads and 2 tails. And the probability of getting any of these possible outcomes is 0.0441. 6 different combinations, each with this probability. And so for n equals 4, right, the probability of getting 2 heads is going to be 6 times this amount. Since 0.0441 is the same thing for all of them, going to add 6 of those together, which gives us 6 times 0.0441 as our probability for getting 2 heads. But there's actually even more elegant ways to do this problem. For example, this 0.0441, you can actually reduce it in terms of probability of getting j successes in n trials. So if j is the number of successes, and n is the number of trials, and p is the probability, and we're looking at this problem we had before, right? The probability is 0.7 of rolling a heads, of flipping a heads. The number of successes that we are looking for is j, and so that ends up being 2 because we want 2 heads. And then the number of trials is 4 because we are doing 4 total flips. And so we need to get at least 2 heads. So it's going to be 0.7 squared, which is these 2. And then we need to get at least 2 tails, which is going to be 4 minus 2, so that's 2. And then 1 minus 0.7, which is 0.3. So that's what we have here. And that's going to come out to 0.0441. And so you can see how this would work for wanting to get any number of heads, right? If we wanted to get all 4 heads, then this would just be p to the fourth and 1 minus p to the 0th. If we wanted to get all of tails, this would be p to the 0 and 1 minus p to the fourth. So this is a very elegant equation to always get us the total probability of, or the given probability of one of these combinations. And so the next thing we need to be able to calculate is the different orders of j successes on n trials. I'm not going to go into how we derive this, though there is a very elegant math solution to it. For now, you can just sort of know that it's n factorial over j factorial multiplied by n minus j factorial. Factorials denote a 2 factorial is 2 times 1. A 3 factorial is 3 times 2 times 1. A 4 factorial is 4 times 3 times 2 times 1. It's a really common math term for dealing with combinatorics. You should probably be familiar with what it, or get familiar with what it is if you've never seen it before. It's a very useful concept. As for deriving where this particular equation comes from, don't worry about it. Just know that you can use this to quickly figure out the number of possible combinations that you can have of a binomial distribution given the number of trials, or the number of flips you're going to do n, and the number of successes that you want j. And that leaves you with this binomial equation, right? With one part that is the total number of combinations you're dealing with. The other part is calculating the probability of each one of those combinations, and multiplying them together is going to give you that probability of any number of successes on any number of trials that you want to calculate with any probability that you want to enter in. All can be calculated very quickly and very easily without having to do a full tree. Granted that it is a binomial distribution. So there's no need for you to memorize this. If you ever have an exam, you'll be able to look it up, but it's good to know how to use it. Okay, so if we revisit our probability trees, now on the right is the probability tree we did before with probability of heads is 0.7. Now on the left, we can plot out the possible number of successes, 0, 1, and 2. And using the binomial equation, here's the probabilities of each, and it generates this distribution. And this is what we call a probability distribution. If we had a 50-50 split, now that those blue dots would change in place, right? And we have a different probability distribution. And this can be easily extrapolated out using this equation. So here's for 2 tosses with 50-50, 2 tosses with 70-30. And then it gets much more interesting as we go up, right? So now if we did 10 tosses, right, the probability curve is much smoother, but it's also much lower because there's, more possible options. So therefore, all of the probabilities of getting any individual option goes down. And now if it's skewed 70-30, we see that this gets pushed over to one side. And for 20 tosses, we have this really smooth gradient. And for 20 tosses with the 70-30, now it's pushed over to one side. So as you can see, the more and more trials we do, the smoother this curve gets, and the more it starts to look like a very continuous distribution. But it's not. It's always discrete because there's a set number of trials. So we'll talk more about distributions and what discrete and continuous is in the next video.